Okay, so in this lesson, we're going to be learning about more terminology. The first one are state functions. Okay, state functions are properties that which depend only on the initial and final states. Initial and final states. Okay, let me give you an example of a state function, okay? An example of a state function is altitude. So if this is the base of the mountain, and this is the top of the mountain. Let's pretend it's Mount Everest. Can somebody look up the height of, or the elevation of Mount Everest from the base to the peak? 8,000. Let's just say 900. Okay, let's just feet. Okay, so that number is a state function because if you take a helicopter, it'll go straight up. It's still you would still went 8,900 feet, right? Oh, meter. Sorry. Yeah, that's not, yeah, feet is not very much. Okay, or if you rode a bike and you went zigzag like this, how high is Mount Everest? 8,900 meters. So that never ever changes, regardless of how you get there. That's what a state function is. See that? So, do you think energy is a state function? Yeah. So when we did the experiment here, where we gave off the heat from the permanganate and the glycerin, the amount of heat that came out is not going to ever change. Does that make sense? So energy is a state function, and the reason that is because of this. So let's say we drew an energy diagram. Okay, let's say this is glycerin up top, GLYC, and KMNO4. Those are the two, right? Two reactants and products. Two reactants. The energy is stored inside those bonds, and that energy is a certain amount. Let's say I'm just making up this number. Let's say it's 10,000 joules. That number is never ever going to change. Okay, whatever is stored in the bonds is what it is. And then when these become the products, whatever the products are, you get some CO2, you get some water in there, you get some whatever it is you make. Those molecules also have energy inside them. Let's say it's 1,000 joules, right? That's 1,000 J. I know it's hard to see it. So when you go down the hill, how much energy did you give off? 9,000, right? It goes from 10,000 to 1,000. So how much energy did you get off? 9,000 joules. Do you think that energy will ever change? Okay. What if we put something on top of that and made it spin? So that would be work, right? That would be W, work, right? And then half of it got lost as heat, so that would be Q. W and Q. Is the total still 9,000 joules? Yeah, so it doesn't matter the path that it goes down, whether you worked or you didn't work or you just lost it as heat, it'll always be 9,000 joules. So what I'm saying is energy is a state function, just like altitude is a state function. Okay, now what are non-state functions? Non-state functions are functions that depend on the path. Okay, an example of this is the distance that you traveled. Did you go zigzag? Did you go straight up? Then the distance that you walked, it will change. Does that make sense? That's the distance as a non-state function, and also heat, because sometimes you can lose all that energy. In this diagram, you can just go down all as heat, right? Or you can use half of it. Does the heat change going down? It may change. So therefore, heat is a non-state function because it can change. Yes? Any questions before we go on? This is important because it's important for you to understand that inside the bonds are a certain amount of energy, and that's a constant. Okay. Here on the right side are just some more terminologies. Exothermic is reaction that what? Releases And remember, you have to think of your system, okay? Endothermic is reaction that gains energy or absorbs, either one, fine. Chemical energy. Chemical energy is energy associated with a reaction, a chemical reaction. An example would be the permanganate and the glycerin that we showed you before. Or burning something. Sometimes you'll hear me say thermochemistry or thermodynamics. Thermo just means heat, chemistry, chemicals, dynamics, studying it. The quantitative study of heat accompanying reactions. Okay? The study of heat and its transformations. Okay? It's just terminology. Okay. So you're gonna hear this word called enthalpy. Everybody say enthalpy. So you don't say the H part. It's just enthalpy. Okay? And that is Greek for enthalpane, means to heat. Okay? And the enthalpy is pretty much the same as the heat that you get in a chemical reaction with no work. So in this diagram right here, actually the change in enthalpy. Do you see this 9,000 joules? This is pretty much the change in enthalpy, is 9,000 joules. It's the same as the change in energy. Okay, so it's just a different name for it. Okay, the reason they're equal is because there's no work ever. Okay, so enthalpy represents the heat absorbed or released during a chemical reaction when there's no work. Okay, let me show you a diagram. So I'm going to draw an energy diagram. This is energy on the y-axis. Over here is reaction progress. So first you have the reactants, and it's going to turn into products. How the reaction progresses. Okay. Here you have the reactants. Let's say it's up here in energy, and then it goes down in energy, and the products is over here. Okay. And the difference between these is going to be equal to Q because there's no work. Okay. Let's go ahead and calculate that. Let's say this is, let me see this. Let's say this is 2, 4, 6 joules. What's the difference there? 6 minus 2, right? Like 4. Q is equal to 4. How did you do that? 4J. How did you do that? You just saw the difference, right? The proper way to do this is you always go products minus reactants. So what's products minus reactants? Products is 2 and this is 6. What's 2 minus 6? Negative 4. Let me just make this bigger. Negative 4 joules. Okay, so the proper way to do that is this. What this is pretty much called the change in enthalpy. The difference when there's no work. Okay, so the formula for change in enthalpy, delta H, is equal to the enthalpy of the products minus the enthalpy of the reactants. Okay, what is that? What's the enthalpy of the product? 2 joules. What's the reactant? 6 joules. What's the change in enthalpy? Negative 4 joules. So you just have to pay attention to that. Okay. So don't be confused. The change in energy is the same as the change in enthalpy, and it's the same as Q because there's no work done. So they're all interchangeable in this case. Okay. Any questions so far? Okay. Next, Endothermic reaction. Okay, let's look at this. I have water molecules here. And look, do you see the subscript right there? What does that say? L. So the solid, so there's hydrogen bonding between them. The solid looks like this. You see it kind of moving, it's vibrating. The liquid is like this. They can move past each other, but there's still intermolecular forces. And the gas, the intermolecular forces are totally broken. You see that? So which is more energetic, liquid or gas? Gas is always more energetic. Okay, so when you're drawing the energy diagram for this, you're gonna do energy diagram, put energy here, put the unit, whatever you're using. We're mostly gonna be using joules. You're gonna write the reaction progress on the bottom. So I'm gonna say reaction progress. So what that means is in the beginning, you have reactants, and the reactants will turn into products in the end. And then you have to think, which is moving faster, water liquid or water gas? Water vapor. The gas is moving faster, right? So put the liquid down here because it's moving slower. It has less energy. And then put the gas way up here. You see it? So this, and you're going to label it. Make sure you label it H2O, parenthesis, liquid is the physical state, and this is H2O, gas. Elena, are you doing okay out there?
Yeah.
Okay. You can stop me if you have a question, okay? So from a liquid to gas, you have to climb a hill. So that means I don't have that much energy. You're going to give me energy. I'm going to have more and more and more and more and more energy until I become a gas. You see that? You see it? Do you think this is endothermic or exothermic? Endo. Endo means heat goes in. Does that make sense? Okay. And the way I know is going uphill. Of course, you didn't have that much energy. Now you have a lot in the end. So you had to put energy in. So now the delta H would be equal to products minus reactants. So what's the, oh, let's make up numbers. Okay, I'm just going to do 2. These are just hypothetical numbers, just so you can see. 2, 4, 6. What's the enthalpy of the, what goes first? Products. What's the enthalpy of the products? 6 joules minus reactants. 2 joules equals 4 joules. Now let's analyze this. Four joules. Is that positive or negative? Positive. Why is that the right sign for delta H, for Q is positive? Yeah. What does positive mean? Yeah, you're putting energy into the system. It's becoming richer in energy, more money. Let's say. Okay. So this is your delta H. In the lab, since whenever we measure heat, it's also going to be equal to delta H. They're the same. So, oh, no, I'm sorry. So if you, in the lab, we always measure heat, right? So whatever heat you measure, it's also the same as delta H. So if I say, what's the heat? You say 4 joules. What's delta H? You say 4 joules. What's the change in energy? You say 4 joules. Same thing. Okay, your turn. For this one, you're going to draw an energy diagram for turning liquid into solid. So what are you doing when you're turning liquid? So liquid's like this, and you're going to go like this, right? You're slowing them down a bit so they're vibrating in place, not moving past each other, right? And make up numbers. Give me an hypothetical delta H or Q. Got it? Go ahead. Pause. Okay, so we have draw this. Reaction progress. Reactants go into products. Energy over here. Which is going faster? Liquid. Liquid, right? Liquid will be up top. H2O. Make sure you label it. L. Okay, and then solids going slower, H2O solid. And that makes sense when you freeze something. Do you put heat in or do you take the heat out of it? You're taking the heat out of it, right? So it has used to have a lot of heat or energy, a lot of energy in the beginning, and then you take it out and it has less in the end. Okay, and then you make up numbers here. Let's say this is 2, this is 4, this is 6. And then so delta H would be products minus reactants, which will be the 2 minus 6 joules is equal to negative 4 joules. Okay, so when delta H is negative, what does that mean? Negative means exo. Okay, heat is leaving. Okay, so here's some any questions so far? So here's some examples. Yeah, I added a couple things here. This match is burning, so let me do the first one. A boiling water. So think of the water. If you want to boil the water is a system, okay? You have to think of the water as a system. When you want to boil it, do you have to put the heat into it or out of it? Into it. So boiling water it is endothermic, okay? Go ahead and finish the rest. Okay, let's get answers. All right. Oh, melting butter. What do you think? Yeah. Condensing water. Ooh, that makes sense because condensing is like it's a gas, and then you have to take energy out of it to condense means come together as a liquid, right? So you're removing energy out. So condensing water is exo. Freezing carbon dioxide. Yep. A match while it's burning. Exo. While it's burning, it's giving off heat. Yeah. Like when you initially give it a spark, then that would be endo. Yeah. Ammonium nitrate and water. This is called a dissolution, okay? When you're dissolving something, the beaker feels cold on the outside, okay? If the beaker feels cold on the outside, what is it then? No. On the outside, it feels. Now think of the system. The system is the ammonium nitrate and the water. It has to be endo. Yeah. Does that make sense? The heat went in, so to you it feels cold because it's like leaving your hand. And then this one, it feels hot on the outside, so the heat is coming out. Yeah.